Welcome to the second part of the MLIR running programs mini series. So in part one, we saw how to write a MLIR function and then call it on our terms and actually obtain the output of the function, right? Or like the tensor that comes out of the function. So in this part, in part two, we are going to look at passing inputs to functions. So hopefully this is a short part because we have done the groundwork for this in the last video. Let's get started. Part two. So this time I'm having a single MLIR file. This is even easier than before because it's going to take the two arguments for addition as inputs. So arg0 and arg1, and it's going to return your result output. And like before, we have added the LLVM emit C interface attribute so that I can get the C wrapper. So this part is very easy. Now let's look at the main function. As before, we'll compile down that MLIR file into .ll, and then from .ll, basically using MLIR translate, and then we'll use, maybe I should just show this for my file. So you see the logic is as before, all of these passes are the same. So the first portion is exactly the same. We're going to convert lower down to the lowest form of MLIR and then translate it down to LLVMIR and then again compile, right? So all of these parts remain exactly the same. Nothing has changed. If we go back to our main, let's see, there are going to be changes here now. So the first thing you see is the wrapper has actually changed a bit. Now we are going to take our two inputs and our one output. All of these are passed into this, basically this wrapper function, right? And the important thing here to note is the result is the first argument. I spent a bit of time trying to get this to work. Of course, if you look at the intermediate LL file, you will be able to find this out immediately. But the result is the first argument and not the last argument. So in this case, it's result A and B, right? That's how you have to call it. Now, last time we had a very simple job because we just basically created an empty memref descriptor and then we just passed it in, right? So we are still going to do the same thing for result, but input one and input two, this time we're going to feed the data in from our C++ program on this side. So we'll have to create the structure of the right shape and right parts for it to actually make sense for the MLIR function. So let's look at the easy things, right? So I mean, we know we can basically go with offset 0 as before because we're going to put data at aligned boundary. We know exactly the sizes and the stripe. So this part is the easy part, right? So if you go to the code below, you will see this portion, this code here, which is just basically setting for both inputs because we're just doing add, they're identical. We are setting the sizes to what we expect it to be, right? 2, 5, 2 cross 5, and stripe just 5 cross 1, right? And so now really the tricky part is in getting the other two pointers right, allocated and aligned. So like I mentioned before in the previous video, basically they're same, not the same pointer, but they point to the same region in space with a little bit of delta. Allocated is the where you just allocate memory from, but aligned is the 64 byte aligned location. And this is apparently what that code expects. So that's what we have to do, right? So what I'm doing here is very simple. Basically, I'm going to start with setting number of bytes that we need, calculating that. So it's basically 2 cross 5 into float 32. That's the raw number of bytes we want. We're going to add up to 64. Actually, this can be 63, I think. We're going to add up to 64 bytes so that we have more space because we have to find the aligned address. So then what I'm going to do is I'm just going to create a char pointer. I'm doing this because I want access at byte level, right? So I want to play at byte level. If I make it a float pointer, then if I add things, it will start moving by 4 bytes at a time. So that's why I'm just creating a char pointer of this size, the full size, right? And the allocated pointer is going to be very straightforward. We're just going to cast it to float pointer and then save it in allocated, right? So that's the easy part. So for aligned, we need the first address that is actually 64 byte aligned. So that's what the code you see here is for. So it's very straightforward. You just take the address of your starting point, right? And then the percentage 64, we get that delta, subtract it so that we know the gap, and then add that to the current parameter. So basically doing all of this, you're going to have a point, the first pointer, which is 64 byte aligned, starting from the current address, which is our starting point of allocator, right? So we repeat this exact same logic once for the other tensor, the second input, right? And once we do this, we are going to fill in values. So we have input 1, So basically, we don't care about those first delta bytes between allocated and aligned. Those are going to be just empty. From aligned, because we have 10 entries, 2 cross 5, we are going to save the value 2 in this case, 2.0, right? And similarly, we're going to save the value 3 in the second input. And then we call this function. The only thing to keep in mind here is result is the first argument. All three are statically allocated tensors, so I'm just passing the address so that we have pointer access there. And finally, I mean, just run this. Once we run this, we're going to have the result in the result tensor. And this is exactly as we saw before. You can just print the sizes and shapes. So basically, I just run this straightforward stuff. I'm going to go into part 2 and make. So this is the lowering part. And let's also compile. So this will give us the main binary and run this. And we see the results like we expect, right? So the output is 2 cross 5, strides 5, 1, and the result is all 5 because we did 2 plus 3 this time. So this is a very straightforward addition from the previous part. What we have to do is just manage our input tensors in the right structure and the right way of aligning. And then we can call any function which takes tensors um, directly, right, via this wrapper. So this is hopefully the like very simple. So basically we have done running of MLIR functions with input and output. And in the next two videos, basically we will go back to Alexander Singer's tutorial, take his example, and then try to do some comparison of whether results are fine between the different approaches with different lowerings, the optimizations, and also then compare performance, right? So these two parts hopefully give you the basis of running MLIR functions from your C program.